which is what Aviso used to be, which is not free, and I don't have, I think it can do a lot of stuff. It also has simulation tied to it, but it's not free. There is Python in and of itself is not good at 3D visualization, but something that has emerged recently is Plotly and PyVista, and they're worth monitoring. So soon enough, they're going to become really good. So that's and then there are comments on ImageJ and Fiji. No matter what, you're going to see hardware is very important for 3D data sets because they can take a lot of memory. If you're looking for a personal computer that does visualization, then pay attention to video cards, and also look for gamer machines. That's what they do, visualization. So gamer machines will typically be equipped with video cards that can do the best job. Texas Advanced Computing Center has an entire portal, 2 parallel computers that do visualization. So that can tell you that that can take a lot of hardware. Okay. All right. Okay, so let me allow James. Do you want to take over? Sure. So do we want to? Where are we? We are, I think, right on time in terms of the agenda for start of the second part. Let me know if you need a break. Otherwise, I think we can just keep going.
All right, how does that look? Does that look okay?
Looks good to me.
The Zoom view is always a little bit strange, but I think I can.
Okay.
Hopefully it doesn't, squish.
Well, it's better when you actually just isolate the window you want to show, but then if something pops up, it doesn't show. So, yeah. Hey.
I'm doing it this way for a reason, and that reason is because I'm not disciplined enough to guarantee that I won't click away from this window. But I think I'll be all right. So I wanted to comment a little bit on what Masha is saying as well. My experience is that Python is really useful for interacting with data, for sort of changing data and reprocessing things, making sure you understand what the data is, doing quick checks and viewing slices and so forth. But if you really want to create a 3D visualization, the sort of dedicated GUI applications are the way to go, because digital raw data is pretty big, and rendering that is computationally intensive. And that's not really the problem that Python was built to solve. Whereas, ParaView and Visit and Dragonfly and these applications that were designed specifically to make really nice 3D visualizations are going to really outperform anything that you can do in Python, simply because they've really
that's what they're made for.
That's what they're made for. And the advantage to Python, though, on the other hand, is that you can interact with all different kinds of data very easily. There's so many packages out there that do things, way beyond what we'll touch on in this course, but things you can just go out and download where someone has already solved a problem that you might be trying to solve, and you could just use their code. So the real advantage of Python comes from the add-ons that people have created for it. And if you actually want to talk about visualization specifically, a lot of the visualization software, ParaView and Visit, and they actually have Python APIs, which is basically just a way to say that they've got function calls that you can interact with from the Python command line to do visualization. So if you're familiar with Python and you want to do visualization in Python, or you want to script visualization so that you can process video data and so forth, you can use the APIs for ParaView or Visit or other visualization applications, and it's very interoperable with Python. I think Python's it has advantages over ImageJ because ImageJ is implemented in Java, and I think just doesn't quite perform as well in a lot of cases, whereas Python is running compiled C code for a lot of things. But anyways, my experience is that, Python is great for doing quick checks, but for 3D stuff, find a tool and learn how to use it, and you'll be glad that you did. And I mean, you'll wait a long time for things to render if you do it in ImageJ or Python for 3D stuff. And, the dedicated visualization applications are, quite a bit better. So having said that, now I'm going to do some 3D stuff in Python. So, so I use Python a lot, and I actually use Jupyter Notebooks a lot for checking simulation data. If I have a simulation running on a, like a high performance computing machine, I can check that, the image data that I've got on that machine, is actually there, and that it all downloaded, and then I know what the range of values are and all of those things. And, a lot of HPC centers are starting to support it because people use it for those kind of applications. So I think it's really a great tool for interacting with 3D data in that kind of context, because having a browser, obviously web browsers are designed to interact with data that's not necessarily on your local machine. So, if your data happens to be, on a cloud system or an HPC system, any kind of remote server, the web interface is a really handy way to, just quickly look at your data. So in this lecture, we're going to go through a lot of similar concepts to what Masha talked about in the first part, but we're going to focus specifically on 3D data. So for 3D data, there's a bunch of different formats that people will use. And, if you look on Digital Rock Portal, you'll see stuff that's TIFF images or just raw binary files. And, if you go beyond the Digital Rock space, there's a million image formats for 3D data. And a lot of disciplines will even have custom formats that they use. And a lot of times they are just raw binary files with a header, but interacting and dealing with 3D data is, can be a bit more of a pain simply because of the different formats that people use. And that's what Python is really great at, is that if you find data that's in a strange format, you can almost always find a package that will read that format into Python, and then you can write it out in any format you want. So if you have, if you understand how to get data into a Numpy array, which is what we're going to, talk about here, you can convert it into any form that you want and just work with that and feed, other forms of visualization software or what have you. So I think that that's the thing that for me, I really appreciate from Python, is just the fact that any strange format that somebody's come up with and shared data in, you can usually work with it. So, that's the, that's where I think there's a real advantage. So if you're interested in learning more about 3D plotting, there's some links in here that'll, go into, a lot more detail that we can cover in these sort of simple examples. But at least I think with the simple examples, what you have is a starting point where you can, have something that works and that you can customize to sort of do things that you want to do. So first section here is importing the modules that we're going to be using. So as before, we have NumPy and Matplotlib. We'll show some functionality for those, and then this package called MayaV, which allows you to do reasonably good 3D visualization in Python. As Masha mentioned, there's some version issues. So if you're using, I think, Python 3.8, or if you're on a Mac, it may not work exactly the way it's intended, but it is a fairly good visualization tool. So to install it locally, if you're using an Anaconda Python, and I'm running Anaconda 3.6 on my machine, if you run the command conda install MayaV, it should install the software so that you can use it. And sometimes when you're installing packages, you'll run into, conflicts and so forth, because everybody's local environment is a little bit different. and the packages, within your environment have to be consistent. So if you have problems with your environment, Python does provide virtual environments, which we're not talking about today, but that's the way to solve, usually if you have an environment problem in Python, a virtual environment will get you around it. So basic review of 3D data ordering. So I meant to say this. So first, once you've got the MyIV installed, you import the package. So you're going to import the MLab package for the examples shown here. There's a few other, there's other things in there I think that we won't get into. So all data on a computer is stored as 1D data. So, the memory of a computer, the disk is, it's always reading a 1D stripe of data. So when you take a digital rock image, irrespective of whether it's 2D or 3D or even 4D, it's going to be sitting as a 1D strip, on the physical sort of hardware of the machine. So it gets read, first off of the disk as this stripe, and then that stripe has to be reordered into a 3D, into a 3D array. The order that you do that matters, because if you put the wrong index first, it's going to jumble the data up in a really strange way. So you have to know how to map this 1D stripe to some 3D array. So in our case, we're using, and when you work with raw binary files, by the way, this can be a real problem, because if somebody shares a raw binary file with you and they don't tell you the dimensions, how do you know how to map it into a 3D array? It's just going to be this 1D stripe of data that you read in, and you have to, back it out. So, and that's a problem that having a header file will solve, because a header file is basically giving you metadata about your image. So something like netcdf will have metadata that tells you how to actually read it. And so then the software that's reading something like a netcdf file or a TIFF file will know the structure of the data that it's reading, because it's actually embedded in the header of the file. But when you work with raw binary data, that information is not necessarily embedded. Now, obviously in Digital Rocks portal, they require people to attach that metadata to their project. So you should be able to get it out of the project if you're working with stuff from the Digital Rocks portal, which is obviously really important, because otherwise, you can figure out what the dimensions are, but not quickly. It's not a fun process to go back and figure out the order of things. So in this case, we're just going to set up a simple NumPy array. So we have the number of slices, the height, and the width. And the number of slices is basically your third dimension. And then the height and width are your 2D dimensions that you would think of for an image. At least I think that's the way that I think about it. And so then we're going to create a NumPy array of zeros, and slices is the first argument, and then height and width. So the way this will get laid out in memory is actually the backwards from the way that it's ordered. So the values in width are contiguous in memory and on disk, and then you have a stride of width values in the height direction, and then again for the slice direction. So if you write a loop, for example, like if you wanted to write a for loop to loop over this data, this would be the outer loop, and this would be the inner loop. So the inner index should go over width, and the outer index should go over slices. And that's just a convention in Python. If you go and work with a C code or something else, other people make other decisions about how to lay things out. But ultimately, that data is stored on disk in a particular order, and you have to read it in the order that it's.
If you started and see if some of us older people did, then you're kind of getting annoyed with that convention.
I get annoyed with all conventions, and when I write code, I write it as 1D code. Unless I'm working with NumPy. So Yeah, so this is just going to be an array of zeros, and then we're going to change some values in there and visualize them, right? So we can go in once we have it in an array, and we can access, particular values. We can do all sorts of processing on them, and you can see how these are laid out, right? So let's look at what this code is doing. So here we're just printing out 1, and then these colons just mean, right, you're printing out all those values. So the first thing we're printing out here is, well, I guess the first one is the original one. So the first thing we print out is original, and that's going to print out 2 slices. So it's printing out both, and you see you've got zeros, right? So this is the original data that you start with up here when you have just an array of zeros. So you've got 2 slices, 1, 2, and then each of those slices is going to be 3 by 4. And the way that this will get laid out in memory is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so forth, right? So that's the actual order that the data is stored on the disk when you read the image. If you, I mean, this is just one we've created in memory, so it's in memory. But when you read an image, you have to make sure that when you print it out like this, that's the way that you've read it into the system. So,
and a lot of time when you load images, it could be actually some of this GUI software that, like, you load the image and you see sort of a bit of a scramble. It's probably because, like, you see some structure to the data, but there are some odd stripes through the image. That's probably because you inverted some of these dimensions. So go play with that.
And with a binary file, you can read the wrong dimensions. And sometimes if you read the wrong dimensions, you'll get a weird skew, or it'll look like it's leaning one way or something. There's all sorts of things that can happen when you read a binary file the wrong way. And this is one of the reasons why this quick visualization is so useful in practice, because if you're working with some data and you're processing it, if you can just look at an image, you'll see if you've read it right immediately most of the time. Like, it'll either look terrible or it'll look right. And so it's really, important to just, be able to visualize stuff quickly, like we're going to do here. So now the second value here, we're just going to change one value, and here it's 1, and then we're changing, again, here you see the colons. So where is it changing here? Well, it's changing all these values right here, right? So that whole slice of values is set to 1, and then these are all contiguous, in memory. They're going to be sort of laid out. It's changed all that stuff. And then here's another one where we're going to set just 0, 2, and then this one all to 6. So then you can see the 6s all go on this row here. So, and then we can change the shape of an array. So here we started with a 3D array, and we can map this, to a, 1 by 24 array, because, there's 24 values here. We can map it into 1D, and we see basically how it's going to be laid out in memory, like it would be in a binary file, and how it is in memory. So when we write loops that operate on this array, we always want to make sure that they're going in this order. Because if they don't go in this order, if they jump around, like say you went from 0, and then you went to the next slice, you went to 1, and then you went back to 0, and then you went back to this one, that's not how computer processors are designed to work most efficiently. So if you ever write a little bit of a code to do that, what you'll see is that it runs, an order of magnitude faster if you access the values in the order that they're laid out in memory, instead of hopping around based on these strides. So that means that, for a NumPy array, you want to sort of inner loop to be over the width, and your outer loop to be out of the slices. If that, that will make sense if you write a loop, and if you test the performance in particular, it'll be pretty obvious that that it's pretty advantageous to loop over it in the order that it's stored. Okay, so now we'll reshape it. I better run this so I don't end up in some sort of yeah. So Now we can reshape it back to the original dimension. So we're going to do it like this, and then make a quick visualization with matplotlib. So we're just going to show with some gray map what these slices look like. So here's the first slice, and then here's the second slice. So what would happen, for example, if we, instead of running it this way, if I did, say, a 4 here and a 2 here, what's that going to look like? So it's going to change the way this data is laid out. And, you know, it's, if it's an image that's actually, you know, stored the other way, it's going to be, you know, it's going to be wrong. It's going to look completely garbled up. And we could do it, in other ways, too, where we, for example, interchange this 3 and the 4. So we do 3, 4, 2, and then, we have another sort of different value that we, or a different arrangement of values that we have. And that's not, really what you want. If you're reading an image, you have to respect the dimensions that.
And there will be no error message, because what does computer know? It just goes in order, and as long as you have, you don't go over the number of values that it has, it's going to be just fine.
Yeah, and I think
plot what you asked it to plot.
If I put in NumPy is smart enough to know that doesn't work, right? So if I put a 5 in there, it knows that it can't reshape 24 values, like this. So it has to be, basically something that multiplies out to 24, which is, at least that's somewhat helpful, because you can't, that rules out a lot of mistakes that you can make. But if you're not ordering it in the right way, then you're going to end up with problems. So we'll go back, we'll do 2, 3, 4, and that's the right way to access this array that we've created. So what is the other sort of key thing to know about the data type is, or about the data, is the data type. So what the data type is, computers store information in binary format, which means that at some level you have a 0 or a 1. And numbers are represented by combinations of these zeros and ones that are usually talked about in terms of bytes. So a byte is just a combination of 8, zeros and ones. So if you take 2 to the power 8, with 1 byte, you can represent 256 possible numbers. So the standard, oops, I clicked the wrong thing. So a standard 8-bit integer is going to allow you to represent 256 different numbers. And those are, for a regular byte, they would be from -127 to 128. So that's 256 numbers, and that's the range of values that you could represent. If you go to an unsigned integer, then you can represent everything from 0 to 256, because you take the space of negative numbers and you exclude it from the set of numbers that you're representing. So these are the NumPy data types. So, if you have data that's stored as a single byte, 8-bit integer on disk, you can read it into NumPy using the corresponding data type, an 8-bit integer in this case. If I take an 8-bit integer and I read it as an 8-bit unsigned integer, there's going to be a mapping between these values where things that were supposed to be, say, 101, 127 are going to get mapped to 255 or something, like that. I think it will map the negative numbers to 255. So you're going to end up with the data being represented differently than it is in the data set. So you have to pay attention to the data type to make sure that when you read the file, it's represented the right way in your data. Now, you could deal with switching an 8-bit integer with an 8-bit unsigned integer. If you visualized it, you'd still see probably the same structure, because it wouldn't garble it up in the same way that it would if you read an 8-bit integer as a 16-bit integer. So the advantage of a 16-bit integer is that now you can represent 2 to the 16 different values. So you can put a lot more labels in your image with a 16-bit integer, but you're also going to use twice as much space. So there's a trade-off between the amount of information that you can embed in a single number and the amount of space that your data is going to take up. And a lot of times with digital rock stuff, if people are just representing zeros and ones, then it's pretty common for people to store stuff as 8-bit integers, and a large fraction of segmented data is represented this way. If you look at grayscale data, that hasn't been segmented, it's a lot more common to use a 16-bit integer or larger integers or even single precision or double precision representations, which are larger, but they allow you to represent more information within a single voxel. So if we did this and we accidentally read 8-bit data as a 16-bit integer, it wouldn't, you'd have an array that was half as long because there's only half as many values in that file. And the values would be completely wrong. They would just be nonsense because you'd be taking 2 8-bit values and stitching them together into a single integer, and you'd end up with, nonsense in your image. So that's the sort of basics of the data type. And there's more information at this link if you want to see, full list of information on what's supported within Numpy. You can click this link. These are the most common types, I would say, and really, I think a lot of times with Digital Rocks portal, it's going to be either single byte or 16-bit integers. Okay, so the other convention that you have to know about is whether or not the number is represented as a big endian number or a little endian number. And what endianism refers to is that is the order that the bytes are laid out. So if I have an 8-bit integer, there's only one way that I can lay it out because there's only one byte. So if I'm representing a number with this byte, then there's only really one way that I can do it. If I have 2, oops, I clicked it again. I'm trying to highlight it so people can see what I'm doing, and I open it. If you have a 2-byte integer, then you could put the first byte first and interpret the number one way based on that, or you could put the second byte first and interpret the number ways, that way. So there's a convention in terms of the endianism that the architecture, the operating system that you're running on, and the architecture have to understand. So most of the data, I think, is little endian now, but it wasn't always that way. And if you get a big endian file and it's not a single byte value, and you read it using a little endian convention, then you'll get crazy numbers that are, like close to machine precision. So you can read more about the byte stuff there, but this next stretch of code will actually tell you there's a command that will tell you what the byte convention is. So as before, we're going to download some project data from Digital Rocks portal. I'll just show you where this project is so we can copy that up and say, go to my other browser window. Some tips for MayaV. So if you're having trouble with MayaV on Jupyter notebooks, there are some tips here. I think there's a link in these slides if you run into problems, but that's worth visiting. So here's the project that we're looking at here. Oops, what did I do? Oh, I downloaded it. That's why.
That's a direct download link. That's why.
All right. So this is the project that we're looking at here. And when you go to a project, the metadata should be included. So there's going to be, some metadata overall project.
This is the sample, yeah.
That's the sample data, and then we need to go down to, which one of these is it?
That's a good question. There's a direct link. There's a direct link in the notebook.
Tell me, right? Images. but it
So
won't.
download will actually go directly to download.
I delete download though, it doesn't go there, right?
No, that's
So-
the fun part. So you have to basically walk over. Let me.
There we go. Well, this is what I was really getting after was this stuff. So when you go to a particular data set, in this case it's an analysis data set. It's probably not the one we're looking at here, but there's information about the image type. So here we have this information that it's an 8-bit integer, and then it gives us the width of the image, the height of the image, and the number of slices. So it's not a coincidence that these line up with what Masha has ordered in there. The width is going to be, your sort of contiguous value, and the number of slices is going to be essentially your least contiguous value, your outer loop, if you were writing code to loop over the image in order.
And if you click, just to add that to, so how to get that direct URL, you actually have to kind of interact a little. So if you go on download file, there will be on the bottom of your web browser will actually, the link will show. Do you see it now? As your mouse is over, do you see now HTTPS at the bottom lower right corner?
Yeah.
You will see the direct download link.
And I left click, and I think if we go to copy link address, it'll give it to you.
You can do that too. So, but it shows up in the browser, or you can copy it. So it's kind of, you have to interact with the download. Now, if you actually want to a more direct way, we do have a large Excel sheet that has all of those, but it has quite a number of entries because some of the files are in slices. So the 3-dimensional image has all of the slices, and each and every slice has a different address. So that makes it yummy to process. But let me know if you need help with finding what this direct link is.
Yep. So in any case, the metadata is important to know, and it's all these sort of essential pieces are here. So when we read this data into Numpy, we just need to make sure that we observe the conventions here. So we go back to our Jupyter notebook. We can see, in this case, it's a different size file than the one we were just looking at. The width is going to be 234 voxels. The height is 234, and then there's 19 slices. And so this code up here is just going to get the file name. Now, if I've already downloaded this file, which I have, I can copy this so that it doesn't, I can just comment this stuff out so that it doesn't download it each time I run it. And, that's, it's not a problem necessarily if it downloads it each time, but if you wanted to work offline and you didn't have internet, you could just comment that out and it would work. Otherwise, it'll hang because it'll try to download it and won't be able to, right? So if you're not on the internet, you can't download the file. So we read the file in, and so far we haven't ordered it. We're just going to have a one-dimensional array because we have these in the notebook, but we haven't actually reshaped it yet. So all data in this case is just going to be a single byte, an unsigned byte, 8-bit integer, that has a little endian type. So this is the little endian type. So if we've done it this way, then we should be consistent with the data type that's listed on the Digital Rocks portal. Now, when we come back and reshape it, as we discussed in the first part, we have to make sure that it's read or that it's ordered consistently. So we do here, we're going to run this, and we see a slice of it just plotted with matplotlib. So we read slices, height, width. Now let's go ahead and just put width first and see what happens. Now it should read it because the dimensions match, so it should reshape it. But you can see now I've got some confusing thing here, and I can do it again. I could just look at that, and then let's change the slice that we're looking at. So let's look at 5 here and see what that looks like. So you can see there that we've got this pretty messy looking thing
It's kind of fun. It's almost like some sort of a biological.
You can tell that there's some structure in this image, right? Because, it's got this repeating pattern, but it's not, it's not right. So, if you're, if you looked at the images,
Like carbonate DNA.
you looked at the images attached on Digital Rocks portal, then you would probably realize pretty quickly that you made a mistake. And if you think, like, I run a lot of simulations on these images, so if I read it into my simulation this way, man, I'd really get nonsense. So it's very useful to quickly visualize stuff to make sure that you've laid it out properly. And so we're just going to reorder this back to the proper layout. So the first one is hold on. So we got to have slices first and width last, right?
Yep.
Right. And when we just, if we go back here, you see.
And if not, you will know quickly.
We'll find it out if we don't do it right. So we'll just go ahead and rerun that. And now we're going back to seeing this slice because I've moved this. So let's move that back and look at a more interesting slice. So let's look at 20 this time. So we'll just look at some slice.
You're over. You have 19, 0 through, you have 19 total, so 0 through 18.
There you go. So there's slice 9, and now we can see this bug in the middle of this image, right?
Yeah.
So we can go through these.
And the rest you cannot resolve. Those are actually beads, but when you see them, they're 1 millimeter. When you see them with CT, you cannot resolve them properly. You see some porous structure, but it's not resolved.
So we can see this bug if we just go through, and we can really kind of figure out where it is. And it's pretty easy, but if we wanted to make a really nice visualization of this 3D structure, this isn't the way to do it. I mean, it's nice enough that you could, put it in a paper, and you could change the color scale, like say plasma. So you can go find different color scales and make it look pretty. But, if you really want to do a 3D visualization, that's, Matplotlib is a little bit limited. So for this next section, we'll switch to MayaV, which is a bit more, has a bit more advanced capabilities in terms of visualizing stuff. So there's some links in here that you can go to if you want to learn more about MayaV, because we're not really even scratching the surface of what these packages can do. So I think here you can see what's in there and a couple of visualizations that they've created. So there's 3 main ways that people will visualize 3D data. I mean, I actually think there's more than that, because you can image velocity fields and so forth. But the main capabilities are ISO surfaces, which are, we're going to
cover next. So
we're going to cover more about that, but they're basically lists of triangles that you can represent. It's a sort of numerical representation of a 2D structure. And then there's volume plotting, and I think Dragonfly has some really nice volume plots in it. And volume plots are really, they can be computationally expensive. So, I think if I try to run it in MayaV, it will probably hang my computer and, kick me offline or something. But so there's those, and then there's sort of just the simple slice extension, but where you're slicing in 3D, so you can slice in multiple directions and see that structure. So that's the example that we're going to do here, and you can see that we can set this slice index. Now, Masha mentioned that MayaV doesn't work great with Mac. So when I run this on my Mac, it doesn't. Well, actually, this is actually. This does work on my Mac. And the interactive visualization does work, but not this particular example. So I switched it so that it would actually use the off-screen mode, which means that it's going to write it into a file. So instead of rendering it to an interactive window. And that can be handy, in some cases too, because then I can just open my file in a browser here. So that's the one that I've rendered with this piece of code, and I think I can go in and I can actually say, all right, well, we'll use this slice index, we'll change it to 10, and I don't want to change that because I'm not sure. Let's see if plasma works. I haven't tried this before. So now I'm just going to rerun this, with a different slice, and we'll look at it again. If I just reload this page, it'll reread the image, and you can see it's now plasma. I can see that bug. And all I need to do to view that image is just put it into my browser. So that's the sort of poor man's interactive visualization, I guess, is that you can use the browser to just view a 2D image that you've rendered. But that's not very interactive, and it would get really, really onerous to do that. So this is where I think it's a lot better to use a tool where you can interact with it directly. So this is an example where you interact with a set of points, and where you see points come up, here's some points, and so now I can turn it, and I could really say, well, I want to see it, in a particular way, and that's my productivity is going to go through the roof if I'm trying to make a really nice looking image, and I'm doing it like this and turning it to see what looks good, instead of coming back up here and saying, all right, well, I don't like that one, I'm going to go and look at 12, and I'm going to use some other color map, whatever it is, and then I come back over and look at it, in this window here or something.
And just to comment on it, so in that set of points is just an example of placing an object, which is called a glyph, in this case, a sphere that has certain size and color to it at a certain location. So that's a specific visualization choice that might or might not make sense with the data. So this is just an example. It's like, here are the points. And then you need to have those XYZs of those points and create them into a grid. And the little code there does that. And so without going too much into detail, that's essentially the summary.
So one place where you really see visualizations with point kind of visualizations for digital rock images is if you look at like the pore size distribution, like they would extract in pore network models, where they'll go and they'll take a maximum inscribed sphere, and they would find that for each pore, and then you get this information on the distribution of pore sizes within a digital rock image. And then people make some really nice visualizations that show this. And that would actually be really a useful thing to do if we consider this one here, or data like it, where there's a big bug. Because if you do this maximum ball algorithm on some data like that, you'll be able to see where those bugs are and how big they are and what the sort of distribution looks like in space. And you can do this sort of ball and stick type models. So, this sort of point style of visualization is, does have applications, and something that, can be important if, you're doing certain kinds of work.
And here there's no example, but you can connect them with lines. I think it's lines 3D command also.
Yeah, so there's a lot of functionality that we won't get into, and that's, if you go to these links, you should be able to get, this one's actually the Jupyter Notebook tip one. So if you have problems with Jupyter Notebooks, go to this tips. That's what I did to get it working with mine, and it was helpful. Although not completely so, because one of my examples didn't never quite work properly. But this one is more, substantive in terms of what the functionality is and how to make that work. So that's point visualizations. Now, if we go back and look at these sort of surface type plots, this next.
We're a little behind time, so maybe this is basically for function, but the examples are working if you have a functional relationship, which in Digital Rocks portal we don't. It just looks great. So that's one thing, but there's an example surface of that same slice that I think is at the bottom.
Do we need to end at 1250?
All together, yes, but kind of you and I, both of our 3D visualization stuff needs to end at 1150, or that's the target, so that we have enough time for questions. But again, I think like there's a plot 2D image slice as a 3D surface, I think is useful for applications to Digital Rocks portal.
And we'll get to more of this stuff. I think for these kind of 3D visualizations, I'll show the slice real quick in Maya V. That's not it. Exit out of this. It won't run the next one until you run the one before, and you have to close that window. So I have to come in here.
There's also MLab, I think it's CLF. One of the first links has some useful commands that you can do to close things up.
All right.
But
Well,
it's good to close image. It's good to close all of the windows.
if I don't close the visualization windows, it won't run the next one. So, all right. Well, let's move on to the next phase so that we don't get too far off our.
Well, well, I can run the last one if it's not running on yours.
Well, it is running, but it isn't popping up there. I know if I close it and rerun it, it'll load. Where is it here?
So basically, there is the main point that you have in there, and there's some actually explanations in the slides that I provided, is that if you're trying to plot surfaces heights over the plane, and it's just a simple functional relationship, then you have to actually provide it a grid of points. And there's two ways to do that. There's sort of matplotlib, which just creates a static image that is embedded in Jupyter Notebook. That kind of always works, but it's not fun because it's not interactive. So and then there's there's example with Mayavi that you can interact. And so all of the advanced visualization GUIs, they do this, that what James is exemplifying. Basically, you can interact with it. But this is there we go. This is the beauty on unresolved data. So it's a little noisy because data is noisy, but it's that same slice we were looking at as heights above the plane. And the one that is well resolved is that VUG in the middle that is black, and the rest, because the height is 0, and the rest of it is noisy because it is it's not a well resolved image. So that's just viewing slice information, the grayscale information, as a height on top of as a surface. And often if you had a fracture and you had aperture, how open that fracture is, this aperture is typically plotted as a surface like this. And for some reason, I could not figure out why color map is not changing in this example.
On this one?
Yeah, it's the color bar is showing in the wrong.
I think
color bar is in the wrong.
I assumed it
color
was
map, so it's carrying some information from before.
I had assumed it was because the range was extreme.
Yes.
Anyways,
I
so
think
those are
MLab CLF closes. Try that. Sorry, I'm answering a chat question.
all right. Well, let's
Yeah, so let's move on maybe to
the next section. I'll stop my share so that we can you can get yours up.
all right. Is everybody still doing okay? I'm intending to kind of maybe after this leave a couple of minutes just for everybody to get a bio break or what have you. Is it okay to continue, or are there questions on what James has just presented?